recording is resumed, and our last speaker for today and the last speaker for the whole conference is Marco Bertola, who will talk about graph connections, wild, which is sounds difficult. Character
wild
varieties.
Is wild, wild varieties.
And generating functions in symplectic geometry.
And I will add that we are friends with Marco for ages, but this is the very first time Marco is giving talk on this conference.
Yes, indeed. And I've never been to Moscow before this conference, and I will have to wait again because I'm there only virtually. But thanks, Clonia, for inviting me. It was a pleasure to give this talk. I also want to thank Misha for saying all that I need to have, all that I need, and in a better way than what I'm going to say. So I guess I have to thank Misha then for that. So then let me get on to the talk. So the talk is based essentially on three works that you see here on the screen. There are three works with mostly with Dima Krokin, and then also with my student Sofia Taricone, and one which is in the works with our postdoc Fabrizio Del Monte. So here are the references. And there are multiple links of whatever I'm going to say with several talks that you have seen. So there are links to the talk of Lin Hui Shen's on the first day, Ilya Gayur, who unfortunately I cannot see in the participant right now. And then, of course, today, Kohei Ivaki. And as you can surmise from my introduction, with Misha Shapiro. So let me start with some very nice geometric objects which we stumbled upon, and probably it has a nice origin which is lurking in the background of the literature for several years, probably several decades, but we could not really find spelled out in the way we are going to present. So this is about graph connections on a Riemann surface, punctured or with boundary, just oriented topological surface of dimension 2, real dimension. So here is a picture. Let me move a little bit. Okay, things around. Oh, what happens? Okay, so so we have a Riemann surface of arbitrary genus, and sigma, we can call it a ribbon graph, right? Which is just an embedded graph on a Riemann surface. Is the same notion that Misha was talking about before. Now, for just notation purposes, let me call E of sigma the set of oriented edges. So an element of E is an edge of sigma with an orientation you choose, right? From A to B or from B to A. And V is the set of vertices. Okay, so now this is a super classical object that I've seen many times in many different contexts, right? But now to this object, I'm going to associate a matrix valued function and a canonical twofold. So the data that I want to define is what I call an admissible jump matrix. And because jump starts with a J, I'm calling this matrix J, is just an more or less arbitrary, subject to some conditions, is a map from the set of oriented vertices to a group. Well, I write G, but really, right? Let's keep then things simple. It's just GLN. So for each edge with an orientation, you assign a matrix with the obvious property that the matrix associated to an orientation and the matrix associated with the opposite orientations are related by inversion. And the most important property is the so-called, what we call at least, zero monodromy or flat monodromy condition. So you take an arbitrary vertex of your graph with a valence bigger or equal than 2. So you exclude the univalent vertices like this one, for example. Right? So those you can think of as punctures of on the Riemann surface. And then, so you have the local picture, you have your vertex, you have several incident edges. And using the first property, you can, without much problem, assume that they are oriented away, pointing away from the vertex. And let's call this J1, Jn. You order them in counterclockwise order. And the condition is that the ordered product of these vertices, these matrices, is the identity. No monodrome. So it's a very simple object, right? That's all that we need. So these jump matrices satisfy these two conditions. And then I'm going to make a definition. To this data, I'm going to associate the canonical, for lack of a better word, to form. Let me call it omega, right? Of course, it depends on sigma and on j, but I will not always bring it around this notation. And it's given by the following simple combinatorial object, if you wish. So it's a sum over all vertices of the graph. And for each of these vertex, you take a sum consisting of the number of legs of the vertex, of the trace, and I'm going to say immediately, just in a while, right? Just in a second, what is this k? K is j is what we know, right? I'm indicating the vertex explicitly, so this is j1 of v, right? For example, dgn of v. And this differential is the differential of the matrix entries of these entries. What is k j is just the product from j1 to j. Oops, sorry for the alliteration. Okay, so in other words, for example, the product is k2. Okay, so what's good about this object is that it's a properties, right? The main property is that it's closed. Now, it's not entirely obvious, right? It's based on the following nifty lemma due to essentially Alexeyev, Malkin, and then also Myronkin, and different combination of these three authors. And if I have an arbitrary collection of matrices, then J1, Jn, no relation within that, right? Just arbitrary set of matrices, and you construct something which is exactly of this type. So we take a form, the sum of the trace of K inverse L dk L wedge J inverse L dj L. It's a two form, and then you take the stereo derivative. So this lemma says that the stereo derivative is the trace of the cube of this matrix 3 times, where mu is the product. So then it stands to reason that if you impose that the product is 1, the form is closed. And so basically this omega is just the sum of all of these pieces. Of course, they're not independent because the same edge, the same matrix J appears at the trail and at the head of the vertices, right? That it connected So it's closed. No, so it gives some sort of, well, at the very least, a pre-symplectic structure on the modular space of these objects. And most practical situation would be symplectic structure. And the second is that omega is invariant under many equivalences of graphs. What type of equivalence, except, of course, the obvious one, which is isotropy, with the univalent vertices fixed, right? Because isotropy, of course, this is a topological, construction. So I already have the pictures, right? So that I don't spend too much time. So there are three types of fundamental equivalences. One is the zipping, right? So if I have two vertices and two edges connecting, and here I have jump matrix J prime, here I have J, I can zip them together into one edge and associate. So I get a new graph, ribbon graph, and also I have to associate with this new edge, the matrix product of these two jumps. Then if I compute the omega, so omega of sigma is and J, and the collection of these jump matrices is equal to omega of sigma tilde. So that's the first type of move. The second is the detaching, attaching procedure, which is the following. Suppose you have a vertex and there is an edge incoming and an edge outgoing that carry the same jump matrix J.
Sorry,
Then
Marco,
yes.
may I ask a stupid question? So you have conditioned that J coincide with J inverse, right?
In this lemma, yes.
If you take J prime, so does the product also satisfy the same condition?
Right, because so you mean when I reverse the orientation, right?
No, when you take when you combine, right? J prime.
No, but okay. So because there are other edges here, right? So there are other J1, etc. Here there are F1, etc. So the product of all of them has to be the identity. The product of all of them has to be the identity, and this is clearly preserved. Right?
No, that's clear, yeah, but you don't require that J is now square of J is 1, right?
No. This is J prime is two independent matrices.
Oh, okay, yeah, sorry, yeah. Mm-hmm.
Right. So in this here you have the same J coming in and the J going out, and then you can kind of detach, right? So this edge, of course, it ends somewhere else, right? It could be the same coming in somewhere else, but the local picture is that you can detach this, right? And it goes off like that. And again, the same applies. The omega of the canonical two form associated with the first graph is the same as canonical full form associated with the second graph, right? So, and the obvious last one that we need is the edge contraction. So if I have two vertices connected by an edge carrying this matrix J0, right? Then I can just shrink this to 0 and I get just one vertex carrying the remaining edges. And again, the two form is invariant. So it has this nice functorial property, this two form. It's a nice invariant of the graph. Okay, so why the terminology of jump matrix? Sorry, let's change color. Why jumps? Because we can think these data define what people in other a local G system, as probably this terminology would be what Fock and Goncharov would use. So they say, see, for example, Lin Hui talk that he was talking about. And so I should probably add flat here, but probably redundant. which in different corner of science, of mathematics, is just called the Riemann-Hilbert problem. So what is that? This Riemann-Hilbert problem. It consists in typically, right, would be consisting in finding psi of z analytic. Now you have to set up also some analytic conformal structure on the surface, analytic of the contour. Now for each edge, you have a left side, which is typically denoted by plus, and the right side, which is denoted by the minus side. And so on this edge carries this jump matrix, and you want your boundary values of psi to be related to each other by this relation. In the general Riemann-Hilbert problem, the jump matrix may depend on z, right? But for us, in this simplified context, it's just a constant matrix.
And Marco, just a quick question.
Yes.
J of z, of course, depends on z, but before, earlier on, what?
Yeah, that's what I just said. So in the general setting of the Riemann-Hilbert problem, J depends on Z, but here is just a constant.
Okay, that's what I wanted to know.
Yeah. So one can interpret this type of data as really as a graph connection on the dual graph, in the sense of graph theory. Right? Then J. I guess you have to associate each edge its dual edge, and by extension, J hat will be the connection associated to the dual edge is a flat graph connection. So on what?
How do you deduce the dual J's from the original J?
I'll draw a picture in a second. On C minus the univalent vertices. So Y is flat. What is flat here? So you have your graph sigma, right? And the dual graph, it's just like that, right? And then, well, this will one vertex for each phase, and one phase for each vertex. So the phase of this dual graph corresponds to the vertex of the original, and so
that's just the product. J hat is just the product.
So J is this, right? And J hat is just J check is the matrix on the edge that crosses the original edge with the appropriate index that determine positive index intersection. So when you write the zero monodromy condition on this graph, right, which is the product of these is the identity, is the same as saying that the graph, the holonomy around this face is trivial. Okay. Of course, you can't if you have a univalent vertex. That's since we don't have the condition, the dual graph here is the dual phase, right? It's just a loop. But there is no around this loop. There is monodrome. There is a line. So really, is a flat connection on the dual graph. And maybe I should add that in the abelian case, so GL1, right? So JE is just E to the lambda E, right? Where a lambda of minus E is just minus lambda of E. Where lambda is just in the here context is a complex number, arbitrary complex number. Then this omega has exactly the same combinatorics as Kontsevich symplectic form well, I just say the famous paper on Witten Kontsevich. Well, one of the famous papers of Kontsevich. So the famous paper on the Witten's conjecture. He uses this to define the volume form over which integrates to set up this gizmo random matrices. Okay. So in that context, of course, these two form is just becomes just a two form in V lambdas with constant coefficients. Right? Exactly the same type of combinatorics. If these lambdas are actually positive in positive numbers, of course, associated to an edge, a real number, right? But one way it will be positive, and the other way it will be negative. They are essentially the oriented Strebel length associated to the ribbon graph, to the Jenkins-Strebel differential associated to the ribbon graph. Okay, so now that gets to application of this nifty sorry, I had it. I had it already here. So first of all, character variety, I'm lucky I don't have to redefine, but it's just, as Misha very aptly said, is the pi1, the set of maps from pi1, the homomorphisms, pi1 to GLN, modulo the adjoint action of the group. What is the, now, I cannot give such a clean-cut definition of wild character variety in this same language, so I'm going to use some kind of proxy for that. Right? So the character variety, so example in CP1 minus punctures, the character variety is the same thing as the monodromy data of a Fuchsian connection with poles at the punctures. Okay, so psi prime equals sum of AJ over Z minus TJ psi. Garnier system, or if you wish, Painlevé type systems. Right? So there is a monodromy map, and that monodromy map gives you modulo, of course, conjugation, because it depends on the base points, the point of integration. But when you compute the monodromy of psi, the monodromy map gives you a point in the character variety. So the character variety is just, you can view it as the modular spaces of Fuchsian connections. Or this part, right? The other part of the modular space. So now, what is the wild character variety? Where wild, and I'll tell you where the terminology is not mine. I wouldn't dare call it wild. So what is it? Is just the extended monodromy map. What in other corners of the mathematics is called the extended integrable systems monodromy map, i.e. monodromy, Stokes matrices, connection matrices. So essentially it's what in the famous paper of Jimbo, Miwa, Wayne in the 80s was recalled in the introduction of one, where the name comes from a paper by Martinet and Rames in 91, where they call the Stokes phenomenon of an irregular singularity, ODE, they call it the wild monodromy. And then this terminology in certain areas is stuck, right? But it really goes back to the fundamental foundational works of Vazov, Shibuya. We didn't call, of course, wild, but Balzer, Urquhart, much earlier than 91. So the interesting thing is that whatever they are both wild or not. They are Poisson manifold, as Misha already basically surmised. So on the character variety, there is the Goldman bracket. And I will maybe write a formula, although Misha was already introducing. So if I have the traces, now the functions that are invariant, the function on the character variety has traces of monodromy associated with the path, right? it's enough to say what is the Poisson bracket. So this is the Goldman, and this is the definition, is the sum over all intersection points. So here is the standard intersection number, and here is the trace of the monodromy of the path that you obtain by starting from this particular point of intersection. You follow the point, you follow the path. So you have gamma, right? It goes around and comes back. And then you have gamma tilde that also. So now you take the homotopy class, free homotopy class of the path that you obtained by following first gamma and then gamma tilde and coming back is a closed loop. They may intersect in other points, right? But still they define homotopy class. So it's not entirely obvious that this is a Poisson bracket. You have to check well, the skew symmetry is obvious, but not the Jacobi identity, right? So this is for GLN, I should say, really. And what is wild? In the wild category, the foundational work was the work of Flash Canoe, really, forgotten for almost 20 years. In the 80s, and basically they were discussing the Planlevé-2 hierarchy. So then Ugalia used this idea, as mentioned before, in this 99 paper. I think that the Mondal groupoid post-dates 99, so this should be really, the bracket that you were talking about, Misha, should probably have Ugalia as a first, because as far as I know, she was the first to define it. And then Philip Boach, in series of papers spanning 2001 to 2007, they generalized to basically a general wild character variety. Okay, and for us, the crucial thing is this theorem. You see that a nice picture is coming up due to Alexeyev and Malkin, 95. Is that, and I'm going to give a formulation of the theorem. That's not the way they formulate, but it's the way we can now reformulate using our gizmo, right? This graph connection. So on the symplectic leaves of the Goldman Poisson bracket, the symplectic structure. So, well, what can I say? How can I write it? The symplectic structure. So the two form that define the symplectic structure, not the two vector structure, is, well, now I think it's 1/2 these omega of sigma, where sigma is the graph and J is the jump matrix indicated in this very picturesque picture. Right? So here are the punches, and then these are the handles, and of course you have to imagine how the thing goes on if there are several more handles. And here, oops, let me shrink a little. Sorry. It's too big. Okay. And so what are here? The matrices M are just the monodromies, and they satisfy the relation in the fundamental group. AJ, BJ, AJ, BJ. I think the inverse goes here. Is the identity. So just the M's, A's, and B's that you see are arbitrary matrices satisfy modulo conjugation, and MJ is CJ lambda J, CJ inverse. This is diagonal. And actually, these are the Casimir's. The entries, the eigenvalues of M are Casimir's. And okay, there are other formulas that relate P's and D's to A, but I'll leave it, they paid, right? So you take this graph, it has several types of vertices, right? There is this one, which is the most important. And then there are these two types, right? Of course, one for a pair for each handle. Then there are these vertices, and they all contribute to the two form. And then if you write it out, this two form, which I'm not going to, right? Because it's an exercise at this level, since I've defined it in general, you will have several contribution, one for each of these vertices. And the theorem that they prove can be interpreted as saying that it's a post-interpretation. They wrote the formula, and Dima and I were just reverse engineering what is the graph behind this formula, now that we know that it comes from the graph. Okay, and that is the graph.
Marco, can I slip in a question?
Yes, of course.
So you are relating this graph connection to the Goldman bracket. Symplectic structure. But when you're really looking at, let's say, the Schlesinger system, you have another, a Poisson structure on the space of connection.
Yes. John, you are stealing my thunder.
Well, so my question obviously is that's the third Poisson structure, and how are the three related?
They are the same by the monodromina. It's kind of a little other story, right? But I will mention that in a second, in fact. Well, maybe 2 minutes, 5 minutes. Okay, so in the paper with Dima, we basically wrote the convenient parametrization of character variety using a third type of graph based on triangulation, etc., where you can use the so-called launcher of coordinates, which give you free parametrizations of these constrained manifold. That's a way of thinking, right? But I'm going to give some simple example of wild application of that. So the two applications that I want to give are examples, right? Two examples in the wild class. Okay, so of course I have to write it, born to be wild, with, of course, the due reference. So one is the flash canule example, and the other is the Ugalia example, which is the same as the Bonda groupoid. And of course, there's a paper by Leonia, Misha, and sorry, I forget the third author. There are two papers, one by Leonia and Misha, and another is also a third author. Okay, Shibo, thanks. Okay, so let's look at, I want to give a general, right? So we'll just give a nice example where things are under flash. Too many vowel consonants. I never remember the spelling. And
sorry, for these two examples, so flash canule is just rank 2 polynomial connection?
That's correct. That's exactly correct. So we have an arbitrary.
Ugalia is what?
Ugalia is Frobenius manifolds.
Ah.
So this is 2 by 2, right? SLR, SL2, C. So it's an irregular, it's a polynomial. Arbitrary degree polynomial with Poincare rank k plus 1. And let me remind of the notion of Stokes phenomenon. So you can write a formal solution where so T is here T is a scalar, right? Because SL2 is just sigma 3, and Y is a formally analytic solution at infinity. So for formally analytic series at infinity, and the Stokes phenomenon. Oh, I had prepared this. So let me, yeah, let me move things down so that we have them in the right place. Apologies for. Almost so loud. And we have Stokes rays that go from any point, let's say 0 to infinity. There is no monodrome in the classical sense. So there's only pure Stokes phenomenon. So this is pure wild character variety, right? Really pure, the wildest form. So and along each ray, in each of these sectors, there exists a unique analytic function solution of the ODE, which is asymptotic to the formal solution. And when you move from sector to sector, you have the relationship between these two solutions in neighboring vectors is essentially a Riemann-Hilbert problem. So, for example, psi, if this is the sector 0 and this is the sector 1, psi 1 is psi 0 times the matrix 1, 0, S2, 1. Maybe not the most logical indexing, that's what, and etc. And because and then there is also a jump where there's a diagonal jump of the exponent of formal monodromy. And these matrices are satisfy the condition that etc. 1, 0, 1, S2K. There are, sorry, I forgot to say there are 2K plus 2 plus 1. These are the Stokes ray. And this plus 1 is the kind of additional jump of the exponent of formal monodromy that you can place more or less wherever you want. And lambda to the sigma 3 is the identity. So that's our Stokes manifold, right? This is the wild character variety. There's no conjugation here, just this is what it is. So it's a manifold of dimension 2K, right? Because you have 2K plus 3 variables, but then you have 3 relations to dimension 2K, even dimension. So so this object is actually symplectic, and so the theorem in this modern formulation that I will tell you, it ties up exactly with what John wanted me to comment on. Right? If you take so your A here is the matrix, the polynomial matrix, right? But it can be any rational matrix. And you consider this classical R matrix structure, Poisson R matrix structure on the entries of A, and you do the monodromy map, the extended monodromy map or wild monodromy map, you will induce this Poisson bracket on the Stokes parameters. These S's are these entries, right? Which are called this, of course, they're called the Stokes parameters. They didn't actually write it in this neat form. You have to kind of work hard to extract it. The paper is written on a typewriter. It's painful to look at, right? But it is there. It is there. One thing, the result was kind of rediscovered independently by Bolge and generalized, I should say, right? That the core of the idea dates back to the 80s. And now the interesting fact is that
what is lambda?
Lambda is the exponent of formal monodromy. It's this one. It's a scalar, right? It's non-zero. So actually lambda in turn is just e to the t0, where t0 is, it's called, sorry, it's not the exponent, it's the formal monodrome itself. Okay. All right, so now the interesting thing, so I want to make a couple of notes, is that this Poisson bracket holds even without the constraint. So it is a Poisson bracket on this wild character variety, but in fact, it's a Poisson bracket in its own respect. So these S's and lambda, they are not related, even if they are not related by any constraint. This is a Poisson bracket, and the character variety, the wild character variety, maybe let me call it the Stokes manifold, is a Poisson submanifold of codimension 3. Okay, so that this is part of this work with Sophia, student Sophia Tarcone, that I mentioned in the introduction. And the second thing,
did I miss something, or did you define the two form, symplectic two form for this?
No, not yet. So far I'm just saying that this is the Poisson bracket and it is symplectic. And then I'm going to tell you what is the two form, but you can, like any good thriller movie, right? I introduced one character at the beginning, and he's the murderer, right? This omega of sigma is the murderer, is the two form. Where I'm going to tell you immediately what is sigma. So it is symplectic. Sorry, symplectic on the Stokes manifold. Otherwise, it has only one Casimir, right? Because dimension is 2k plus 3 odd. And the Casimir is, well, we described it in the paper. It's some simple expression. Okay.
But did you even define what the wild ribbon connection was?
I'm going right now. So, actually, I don't. It's here. It is this. This is the graph. And this is one vertex. And that's it. The omega associated to that. So let me add it as a third note. The symplectic form is omega of sigma, see above. Right? Where this graph, just one vertex is the simplest that you can possibly imagine. There is 2k plus 3 matrices. The product is the identity, because that's exactly the defining property of the Stokes manifold. You just write
what
it.
What is the wild extension of the graph connection?
What do you mean by wild extension?
Well, you gave the definition of the graph connection for the Fuchsian case, but I don't think you gave it for the wild.
No. I gave the definition. Sorry, the connection, the two form is, I define it independently of any graph, of any Fuchsian or not, right? For any graph. And this is a graph that satisfies my condition, right? It has one vertex, the product of the incident edges is the identity, and I can consider the two form associated with this. And the result is that these two form is exactly the symplectic form. So let me rewrite it, right? It's a sum from 1 to 2k plus 3. Then there is this matrices k, L inverse d, k, L wedge. And here the jump matrices are really more or less the Stokes matrices, except for the last one, which is.
I'm a little confused. The graph I thought was only for the Fuchsian case, and you're applying it now to the non-Fuchsian case.
No. The beginning, I just define an arbitrary Riemann surface, an arbitrary graph, and that's it. It's just as to have.
So there's no additional data referring to this vectors?
No, that's kind of the nice thing. It's simple. Right.
It's the same data for the wild and the non-wild. It's not different.
It's the same. Well, I mean,
The graph connection is
the
given.
graph is always the same. It's always the same. That's why it's nice, because it is versatile. Okay, sorry about that. So here we are. And now, so the goal, well, I'm running out of time, right? So I'm giving you that now the connection cluster algebra. So I have to write some parameterization of the Stokes manifold in terms of log canonical coordinates. And to this long story short, this is a formula, right? As you don't have to read it. There is a formula, and it's simple. Where these y's, so this is explicit expression of the Stokes parameters in terms of log canonical coordinates. Can't be more explicit than that, including, and they are log canonical. In other words, the Poisson bracket written in this has this form, and the matrix is very simple, skew-symmetric matrix, obviously symplectic. And there is, of course, behind this a triangulation. And let me briefly mention what it is. So you kind of, this is the same graph before, right? Where we have exploded the vertex that was at the center into some kind of universe on its own. But to say the graph that you saw before is the total contraction of this one, right? So if I define the jump matrices on this one and the two formulas associated by the invariance of the formula, I take the total contraction will be the same as the one before. And now I have to tell you briefly, well, it's sketched on the side, what are the jump matrices. So on the purple, they are the Stokes matrices. On the blue here are diagonal matrices of this form. On the green, they are anti-diagonal of this form. And on these short diagonals. And on the black here, there is the matrix that Misha was calling L, I think. And here, for some reason, we call A. So as the property, the cube is Y, is the identity. So on each of these jump, there is this matrix A. On this one, there is this one, and so on and so forth. Right? So you read it. And the variables are just associated. Well, there is one which is singled out, right? Which is on one of the green edges, and then the others are associated to each of the vertices. So this particular triangulation that I've chosen corresponds exactly to the formulas I've written here. And then the game is afoot, the cluster algebra game, right? So you know that you can flip edges. And of course, the parameterization will change, but it will be the same type of logic. So I could flip this one by replacing by that. And these y coordinates transform as they should according to the theory of cluster algebras. Okay, and the quiver here is just this one. So, so what we are saying is that the wild character variety of this type of connection is really the cluster algebra of type. So it's a cluster algebra of type A to K with one frozen.
Sorry, Marco, you have 6 Stokes parameters. Does that mean you have some, I mean, what is the degree of the AZ polynomial?
Here, in this example is Painlevé itself. It's degree 2.
Okay, that's why you have just 6 there.
Yeah.
So, okay, so in general, you would have whatever 2n
yes,
plus.
That's correct. Yeah, just sorry, that's is not right. So this is an example. Well, the general would be a polygon, and all the diagonals are hinged on one vertex for this. And then you start mutating, you can get all triangulation.
So for degree n, you would have some kind of, not polygon, a polygram, right? Because you have these short diagonals and so on.
Yeah. So it's then you have an octagon, and so on, right? So for degree 3. and so on.
Right. Mhm.
Okay, so I think I have maybe 10 minutes, right, left because we started a bit late. So I have to prioritize. So maybe I will do exactly what Misha did and switch to the pre-written. Okay. Which I can share later. So maybe let me ask audience if it's okay if I rotate so you see more of that, or it's becoming too small.
That's fine.
It's fine.
Fine, yeah.
All right. So so what about symplectic potential? So the interesting fact is that these two forms that we defined admits both a global and a local potential. I mean, one form whose derivative is omega. By the way, I should have added somewhere this disclaimer that in this talk, 1 is equal to 2 is equal to 2 pi I is equal to plus or minus 1. Right? I don't know exactly what are the signs coefficients. But don't hold me too much on that. So, so the global potential, of course, cannot be global. It has singularities. It's meromorphic on the modular spaces on the wildcard variety, and it's given by what I think I called Malgrange one form in honor of Malgrange because it's more or less hidden in this paper of Malgrange. And so what is gamma here? Gamma is the solution of the regular Riemann-Hilbert problem, right? So for example, in the wild case, you have the Stokes, right? And you have the analytic solutions in each of the sectors. And basically each of these psi j is, you write gamma j, this is analytic, e to the t. So you strip away the singular part, and this gamma is what I'm referring to here. More or less, right? Details are in the paper, but time is short. So these objects, of course, has singularities because, as you know, there are particular values of parameters for which the Riemann-Hilbert problem does not have a solution. But so in other words, this gamma here, as a function, transcendental function of the parameters, is singular at this locus. This locus is the Malgrange divisor. And the important thing is that the singularity, which is really the Pain-Levé property, what I'm about to say, the singularity of this form is not just some wild, excuse me, the pun, singularity is just a pole. So this theta is a logarithmic form. In other words, on this divisor, the singularity is like the differential of the logarithm of a function that vanishes analytically to some degree. This result is in Malgrange and then generalized essentially for what we call the wild case by Palmer in 1999. And the consequence on a geometrical point of view is that the two form is an integral two form. And this is also valid in higher genus, and Malgrange divisor is identified with the non-abelian theta divisor for vector bundles on the Riemann surface. Okay, so that's a global kind of picture, which allows you to say that these two form is integral. So just to say it, in other words, is the fact that it's integral up to coefficients, maybe not exactly this coefficient, but okay, some coefficient, allows you, for example, to do geometric quantization if you wanted to. Now, then there is a local expression for the potential. Since you have log canonical coordinates, and eta is just the logarithm of whatever the coordinates are from Fogg-Goncharov coordinate, then you can, in other words, for each triangulation, let's say, right, or in each chart, you can define the symplectic form, for example, like the symplectic potential like this. Right? So locally is the total derivative omega of energy. And So, so what is the symplectic? Well, that's it. Okay, so now let me, last 5 minutes, briefly discuss about these Gallia brackets. And, you know, I was plugging in a geometric description and then I owe it to you. Right? So briefly, what is this, the setup, the context here? Well, this is the context really of Frobenius manifold, one of the formulations by Dubrovin. And in short, it requires you to study the differential equation. Here is a matrix, is n by n matrix. So where this matrix U is diagonal with arbitrary coefficients, and V is skew-symmetric. Okay, so very simple. It has two singularities, one irregular at infinity, and one Fuchsian at 0. So there is a wild character variety associated with that. So long story short, this is geometric description of Misha's talk. The bonded groupoid is the wild character variety associated to Frobenius manifold. That's a catchphrase. Let me elaborate now. Okay, so the Stokes phenomenon has, of course, two Stokes rays that go to infinity, and then there is also monodromy around the origin. So the graph would look something like this, right? A circle. So there are two vertices, a little bit more complicated than that, but let's stick to simplicity. And there are two Stokes matrices. One here is S, unipotent after triangular. And because of the symmetry, this S2 is just the inverse transpose on the other side, oriented this way. Now here there will be some connection matrix. The monodromy is the total monodromy around the origin is the product. So I think this is the matrix, sorry, this in Misha's talk, this was A in Misha's talk. Okay, that for me is a Stokes matrix, so it's S. The monodromy and the Casimirs are the eigenvalues of the monodromy in the Poisson structure. So the formula that Misha wrote is just the characteristic polynomial. Well, it can be written as a characteristic polynomial of that. He wrote it in just different form, but it's exactly that. He wrote the determinant of A plus lambda A transpose, right? But if you factor out the A, it is exactly a characteristic polynomial of the monodromy. Those are the Casimirs, the eigenvalues. So at the brackets that Misha already wrote, they take this shape. So I don't know if it was serendipity, but when I saw the titles of the talk, I already knew in advance that it would be Misha's talk, right? So I already wrote it in the slides. Okay, so what is the graph that does the trick? And it's here. Okay, well, everything is more. So here are the Stokes matrices, and the parameters are associated with this diagonal matrix, and these three matrices, which in Misha's talk, these were the transfer matrices. These matrices was A1, A2, A3 is the identity. Explicitly, I will not write explicit formula also because Misha was very thorough in the description of those matrices, but they depend on, so these A, they depend on the same set of variables. So they're X, A, B, C, where A, B, and C, I use slightly different indicization. It's greater or equal than 1, and the sum is N. Okay, so there are N, now I don't know, N minus 1 over 2, I think, such variables. And then there are a certain number of variable N minus 1, sorry, associated with this diagonal. And this Q is also diagonal, and these Qs are explicitly written suitable monomials, as written here, they are there to make sure that these are unipotent when you take the product, right? Because this S is the product of these 4 matrices inverse, right? Because of the 0 monodromic condition around this vertex. So here is where the monodromy holds. And for example, here are the matrices written out explicitly for n equal 2 is just a constant. For n equal 3, there's only 1 variable. And n equal 4, there are really 3 variables in the size. It's the most inappropriate moment. Okay. Sorry. Okay. Yeah. Well, so anyway, so when you write out in full, I wrote an example, right? What are the Stokes parameters in the end? They do expression that look like this. Not entirely pleasant, but it's explicit. And the fact is that the 2 form associated with this graph, the same logic as before, right? There are 1, 2, 3, 4, 5, 6 vertices, but then there is some symmetry. So really, this is the same as that. This is the same as that. So if you write out the 2 form, it will be in this coordinate log canonical. And so these 2 form provides, if you wish, the covariant expression of the Poisson tensor that of Misha's talk. So Misha is contravariant. I am in this talk covariant. So that is what I have to say. And I think maybe just to I don't know if I have a couple of minutes. I'm home, or maybe not. Yeah, I think maybe it's time. I wanted to say something about generating function because it was in the title, but maybe it's better if I stop, and it will be in the slides that I will make available later on. So maybe I will stop here, and thank you for your attention. Just let me leave this out here.
Let's thank Marco for the nice talk. And questions, please.
May I ask a question?
Yes, yes, please.
What is written in the last pages of your talk?
In which sense? Oh, here.
Oh,
Well, thank you for asking the question. So I can finish the talk. You want me to? Okay, sorry, I was slow on the uptake there. Yeah.
But, Mark, before you finish, one small remark is that if we scroll up a little bit on the probably previous slide, yes, this is this one, yes. So these structures for A matrices are exactly the structures that we got with Misha.
Yes, right. This is the matrix that I think you called F1, 2, 3 in Misha's talk. This A.
Well, M.
M.
Yeah.
Okay, sorry. Well, but these are the matrices, right? That we also.
But do you see the product like some matrix times some matrix transpose? We have expression for S in terms like S is equal to some matrix like M1 transpose times M2 times some diagonal term to make it unipotent.
Okay, so to be explicit here, what is S, right? So S would be Q, which is diagonal,
right?
A1, which is something that looks like this, right? Appropriate to size. Then there is, sorry, I'm losing the pen. Then there is another diagonal D. Then there is A3 inverse transpose, where A3 is the same.
Where this transpose came from?
This one, right? Because
where it's transpose, yeah.
Because that is to preserve the symmetry of the ODE. The solution of the ODE because it's in SO.
Oh, because you have SO, right?
Right.
Right. I see. Yeah. I see.
Otherwise, of course, this would be independent coordinates, right? But because of the symmetry, the coordinate here and the coordinate there are the same. Just reshuffled, but the same set of coordinates.
Mhm.
So A1 and A3 really depends on the same axis, just so it's written here, right? So A1 if ABC and A2 is just permuted the indices.
Mhm.
And then there is, I guess, Q transpose.
Yeah.
And this Q here is exactly as you said, right?
Yeah,
It's just there to make the uniports. And the meat is only contained in this.
I see.
Right, so that's what I was saying, the geometric interpretation, I mean, a geometric interpretation, I don't know if it's the geometric interpretation we're looking for, that is this. This is the Stokes phenomenon of an ODE, and it can be associated to a graph and so on. It's the wild character variety of that. Okay.
Okay, so now you can answer Misha's question.
Well, I don't know. I feel a little. On the other hand, there is nobody speaking after me. That's okay. So that's the bliss and curse of being the last talk, right? Everybody's tired, but on the other hand, you can abuse the audience in this form. So, well, what I was saying is that we have, what about these generating functions? It's tied up with this fact that I was mentioning of the potentials. There is a global potential, which is meromorphic, right? It is logarithmic Malgrange form. And then there are local potentials, which are given by essentially Fogg-Gonchar coordinates. So here I kind of yeah, so the difference of these two potentials is closed form by construction, because they are two potentials for the same symplectic form. And therefore they define, the differential of a locally defined function, and that is the generating function in the sense of symplectic geometry, generating function of the change of Lagrange polarization in a symplectic manifold. So maybe here is what the formula, right? That we often, on the one side, you have the constant Kirillov-Suryault, which is the same as the Lagrange form in different set of coordinates, and minus the, well, technically is the pullback by the monodromy map of the Fogg-Goncharov or Goldman, if you prefer. Symplectic potential is locally closed, and the theorem, which is what we used in the paper with Dina, is that the isomonodromic tau function of ancient memory, Jimbo, Miwa, Ueno, and so on and so forth, it's really the logarithmic derivative is the difference between these two. Now, here is a little bit misleading to call it isomonodromic, because we are actually interested in the changing the monodromy, right? So this is the way you define the dependence of the isomonodromic parameters, isomonodromic function on the monodromy data. Now this one, forget for a second, let's not get into that. So yes, so that I think I don't want to, really finish the talk. It's big, but that's more or less what I want to say in that context. And well, maybe last thing is that since on this side, this is a local object, right? So it depends, for example, if you think of the situation that I described of Flash-Canua, it depends on the triangulation, right? If you change triangulation, these potential changes, the two form does not, but the potential does. And then that means that this tau function now, it's really a section of a line bundle on the wild character variety. And what is this line bundle is something intrinsic to the wild character variety. In fact, it's something intrinsic to any cluster manifold in some sense, because you can play this game in any cluster algebra and cluster manifold. Right? So you just do a mutation, you get different potential, and the generating function is turns out to be some kind of d-logarithm, Rogers d-logarithm of the variable that you have mutated. And so the tau function, for this reason, is really a section of a line bundle, as when you think of it as dependent on the monodromy data, not as a function of the isomonodromic times. For people in this area of mathematics, it's clear what I'm talking about. Maybe for others, it's not. So, right. So it's a section of the line bundle that Dima and I want to call the d-logarithm line bundle. And the interesting thing is that it's really a line bundle. So the interpretation, the fact that this Lagrange form is a logarithmic form, is telling you that the 2 form is really the Chern class of this line bundle because it is integral. And it's basically by construction. It's in the right. It's in the Deran class of the Chern class of the line bundle. Yeah, that was briefly what the end of the talk. But let me stop there, right? Because really, I'm overstaying my welcome. I feel very much.
Is there a chance for another question?
Yeah, you're welcome, John.
Okay. First of all, I just want to understand. Actually, I have 2 or 3 questions, but I'll state it as one question. I just want to understand. So you gave these 2 examples of the Flash-Canule and the Ugalia, but your setup, your general theorem and your whatever
Canonical 2 form, right?
Yeah, is more general than that. It's applicable to more general non-Fuchsian systems.
Well, the game is the following, right? So if you want you have a more general Fuchsian system on CP1 or an arbitrary Riemann surface. You just have to figure out by yourself, by kind of reverse engineering, what is the correct signal, the graph, and how to place nicely the jump matrices on this graph. But the 2 form will be always the same. It's,
Okay,
I mean, the same combinatorics.
On one case which goes a little bit beyond Ugaglia, namely, I mean, Ugaglia's case for n equals 3
Yes.
is a special case of Panlevet 6.
Yes.
That's the dual form of Panlevet 6, but it's a very special set of parameters. Now, so presumably, if you just push through that example, you can write this special case of Panlevet 6 in terms of your log canonical coordinates.
No, no, that's
a very nice, simple dynamical system in terms of, I don't know how many 3 log canonical coordinates, right?
Well, okay, so Panlevet 6 is just a special case of Schlesinger, right? Gambier. And for Schlesinger, we have said everything.
You're using the dual form. You're using the
right,
non-Fuchsian form.
Okay, yeah.
So
but,
it's not really Schlesinger. I mean, it's equivalent to Schlesinger, but reduced. I mean, it's the reduced.
Right.
Okay, so let's just look at the 3x3 system with a simple pole at 0 and a double pole at infinity. So you must have some very simple way to express this dynamical system in terms of your x's, your log canonical coordinates.
Well, not really, right? Because it's kind of orthogonal direction. The Panlevet 6 equation is the isomonodromic equation. So by definition, these parameters are constant. They are the constant of motion of Panlevet 6.
Okay. Right. Okay, so I guess what I mean is, okay, one level higher, you've got a 6-dimensional phase space. Okay,
right.
And that could be coordinatized by your x's. That reduces in quotients to a 2-dimensional phase space for Panlevet 6. And of course, that's not where you have the x's. But in the 6-dimensional space, you presumably should have the x's as a good coordinate system on that not quite reduced phase space. Whether it is the Schlesinger version, which would be a 4 simple poles, 2x2, or the dual version, which is one pole at 0 and a second order pole at infinity and a 3x3. But that should be a coordinatization of the 3x3 one, if I'm not mistaken, which would give a nice dynamical system. I don't know, a 6-dimensional dynamical system.
Well, okay, but
reduces to Panlevet 6 in this special case.
Okay. Yeah, I see what you do. Right.
But my question isn't just about that. I presume that is doable or that it's implicit in what you do. But there's no reason, is there, to only look at Frobenius manifold case? So the Frobenius,
No, I mean, you can do it for an arbitrary, irregular singularity.
So let's
It's
do
just-
it for the thing. Let's do it for the dual Panlevet 6 in general, not for the special one that is Frobenius, but in general. So the only difference is that your matrix V, your residue matrix at 0, is not necessarily skew symmetric.
Yeah, so in that case, of course, you can, tweak the graph and you just have independent coordinates in these two vertices.
So
But,
I'm asking for
same
that
machinery.
special case. That's a little more general than Ugalia.
Oh,
But
sorry, John. My suggestion is that Leonia
Maybe,
makes
yes.
final final remarks, and then you will be able to continue the discussion after I stop recording.
okay.
Great.
Okay, yes,
Okay.
yes, of course. Again. Okay, thank you.
Then Leonia,
Okay.
concluding remarks.
I hope that most of you enjoyed well our this activity. I slightly, how to put it, slightly hesitate to call it a real conference, because I hope that the real conference will be next year in person in Moscow, and everyone is invited, so please come and we'll see each other in our eyes, not just by names on the screen. So, and I want to actually thank all presenters at this conference and all participants due to whom this became possible. So thank you.
Thanks, everybody, and next year in Moscow.
Yes.
Thanks to our guys.
Thank you.
Thank you to the organizers as well.
Yes, thank you.
Yeah.
So what do we do now? Can we